All right, this mini lecture, this pre-lab lecture for your pet molecule is going to focus on gas chromatography. So gas chromatography is a really nice instrumental technique that parallels TLC quite a bit. And at this time in OChem 1 lab, what we're doing is transitioning towards the use of instrumentation to identify the compounds we have. So GC, gas chromatography, versus TLC. Well, you remember TLC. Basically, you have a sample, and it's caught in a tug-of-war between the eluent that carries it up the plate and the junk on the plate, the adsorbent that makes it stick to the plate. It's the polarity and the molecular weight of your sample that impacts how well it sticks to the adsorbent. So, if it's really, really polar, if it has a really high molecular weight, your sample sticks to the adsorbent. However, competing with that is the developing solvent, the eluent. So that mobile phase is pulling the solvent off of the plate and pulling it up the plate. So if it's a really polar compound, or has a really high molecular weight, it's stuck to the plate and therefore it has a really low RF. Well, how does this compare to GC? Well, as you can see from this table, both GC and TLC have a stationary phase, which is the adsorbent to which your sample sticks, and a mobile phase. So how do those compare? Well, we've already talked about TLC. The stationary phase is that white powder stuck to the plate, either silica gel or alumina, and the mobile phase is your ethyl acetate and hexanes, that eluent or developing solvent. In GC, the adsorbent, what the sample sticks to, is actually a liquid. But it's a very, very high boiling liquid because this whole thing is in an oven. So we don't want it to evaporate. So it's really kind of almost more of a gel, you could say. What pushes your sample through the column? Well, it's not an eluent, it's not a solvent. Now, it's a gas, and the gas is typically helium. The data parallel each other quite nicely. The RF in TLC is how far your sample traveled up a plate. The retention time in GC is basically how fast your sample traveled through the column. But the principles are the same. It's still a tug-of-war with your sample being stuck to that liquid adsorbent and being pushed through the column by the helium. A very important distinction between TLC and GC is that for TLC you do not want your sample to evaporate off the plate, so your sample has to be very non-volatile. Whereas in GC it's just the opposite. It has to be volatile. It has to be able to vaporize so that it can be pushed through the column. Alright, so it's based on polarity and volatility, and you know that polarity and volatility is basically a matter of looking at the polarity of the compound, the dipole moment, and the molecular weight. So all things you know. This is what it will look like when all is said and done. You will have something called a GC trace that looks like this, where the x-axis is time, t equals 0 is the point at which you have made the time at which you've made your injection. You inject your sample into the instrument through a little syringe. It immediately volatilizes and starts going through the tube, and eventually at the end it will be detected by a detector, and you'll see something like this trace shown here. So the data are the time exactly right there at the peak of each signal where that peak is detected. So I have two compounds in this mixture. One at this retention time, let's say it's 3 minutes, and one at this other retention time, let's say that's maybe 2 minutes. So that's what I would report. I have two compounds one at retention time 3 minutes, one at retention time 2 minutes. Now, in your pet molecule, you're not going to get a mixture. You're going to get a single compound. But these retention times are diagnostic, just like an RF is diagnostic. For, say, 2-butanol, 2-butanol has, let's say, a retention time of 2.5 minutes for a particular adsorbent and a particular instrument, etc., etc. So if you get the same retention time under those same conditions, that's a piece of evidence that can say, oh, I have 2-butanol. This GC animation does a marvelous job of illustrating this, and what I will do is speed up the timing so it goes a little bit faster and kind of narrate through it here. So this is an animation made by one of the companies that makes GCs, and it's not a going here. There we go. Thermoscientific. So how do GC columns work? So this thing she's holding is actually probably about 30 meters of the GC column. It's a glass capillary. So this is a blow up of the glass capillary, and what happens is you vaporize your solvent, you syringe it into this column, and it's this white goopus, which is the adsorbent, and here are all your samples. So I'm going to pause this for a second. So what you can see is in this animation I've got, 8 different samples, and they're color-coded. So what you want to watch here is that some of these beads that are indicative of your sample mixture go through the column very quickly. Some of them are traveling through more slowly. So here they are getting pushed through the capillary column, the GC column, by your helium gas. Nothing's happening. I don't see anything happening. Time is proceeding. But eventually, the fastest moving compound, which again is the most volatile and least polar, gets detected right here. You can see the peak for the red ones, now the black ones, and eventually we'll see that these golden ones and brown ones, they're really slow to move through. So what you can see is it's just like TLC. The separation results based on this tug of war between the mobile phase and the stationary phase. And eventually everything will come off and you'll have all these different retention times, this is a beautiful TLC. I'm a GC. Alright, last but not least, you need to know that for a specific column and computerized program, which doesn't apply for your pet molecule, each analyte has its own unique retention time. Alright, so that's how GC works. Now, moving right along, what are these other instrumental parameters that impact the retention time? Because we've already talked about volatility and molecular weight. Well, one thing for sure, just like the adsorbent on TLC, the adsorbent in GC also makes a difference. How sticky does my sample stick to the adsorbent? There's generally 2 different kinds of adsorbents, a polar column adsorbent and a non-polar column adsorbent. And what you can see here is that these are both polymers. They're long chain, really big molecules, but they're still liquids. They're really high boiling. But the polar ones are polar because they have the hydroxyl groups, and so that makes polar compounds be attracted to it and stick to it. Non-polar ones have long, greasy hydrocarbons on there that make them non-polar. The column temperature also impacts the retention time. The higher the temperature, the faster the things fly through. And certainly it's, I think, intuitive that if you've got your helium mobile phase flowing really high and fast, that's going to push the sample through more quickly, and so your retention time will decrease, actually, for both of these. Column temperature goes up, retention time goes down. All right, well, this is the GC that we're going to use in the OChem lab. It's a very simple and straightforward little black box. There's nothing you can do to change parameters. So it's really straightforward. All you need to do is make up your sample and inject it into the injection port shown right here at this arrow. The syringes are very easily damaged, so you want to be very careful with the syringes, and we'll definitely be sure to help you make your injection. You will need to note the parameters. I said there's not much you can change. There's actually nothing you can change, but you still need to know what those parameters are. So we'll let you know what the column adsorbent is, and the carrier gas is air, and basically the flow rate. Okay, so that's GC. There's a separate mini lecture for NMR, but what are you going to do when you get to lab? Well, strategy-wise, you have a limited number of possibilities. You're going to get an unknown, and there's probably going to be 2 other people in your lab section who have the same unknown. Who has them? I don't know. You need to get the data to figure that out. There's 4 pieces of data you'll be getting. You'll be doing solubility classification, which is a good review of acid-base and physical properties back from chapter 1. You'll have to take the GC to get the retention time. The retention times of the standard knowns will be posted on the Canvas page. You're going to take yet another infrared spectrum, and these are infrareds of liquids, so it'll be just like you did for cyclohexene, just put a drop on the plate. And last but not least, you're going to be taking an NMR spectrum, and that's why you need to look at the other pre-lab lecture, because you haven't had NMR in lecture yet. So this is just going to be a little brief introduction. I'm going to take the lab section and divide you up into 2 groups. Half of you are going to do solubility testing first. The other half of you are going to start on the GC, so we don't have these long backups. But I'm also going to set up a line of people, a queue, for you guys to start working on getting your IR. That way, I hope we will minimize our lines. Now, as soon as you have gotten your solubility class and your GC retention time, you should start asking around to find out who else has the same unknown as you. Because once you've figured out, and I'll tell you how many people are in your group, once you have figured out who's in your group and what you think you have, or have narrowed it down, you have to come in and check with me, because ultimately there's only going to be 1 sample that your entire group will take for your NMR. You'll all interpret the same spectrum. Okie dokie. Write-up wise, you'll be getting a worksheet. Each person fills out the worksheet. You need to present the data on the worksheet neatly, and then discuss as per the instructions on the worksheet. Here's a suggested outline for your discussion. Notice that when you start here, that's going to narrow it down. But you're still going to have a possibility of like maybe 4 different compounds. The retention time might narrow it down a little bit more to maybe 2. The IR spectrum might narrow it down to 1, or it might still be at 2. But this, in conjunction with all the rest of this, you should be able to specifically identify exactly what compound you and your group members have. All right, what else do you need to know? Well, at this particular time in our country's history, I thought this was a particularly appropriate quote. All right. Well, it's always good to have a break and go into the lab. So that's where we'll see you.